All right, so if you did this right, you would have realized that what you need to do to compute an expected value, the sum over all values that it can take on, the probability of that value, times the value itself. So what that amounts to is summing over all pairs W and X that are neighbors to V. We sum whether they're either connected or they're not connected, and that's represented by this CWX thing. And we need to multiply that by the probability that we pick that particular W and X. Well, all the W and X's are picked uniformly at random, and the number of different pairings of them is the degree of V times the degree of V minus 1 divided by 2. That's the number of different ways you can pair up a set of size dV. The reciprocal of that is now the probability that we pick any particular pair. But this is independent of CWX. So really we can move this out front and just do it as 2 times the degree minus 1 times whether or not the two nodes are connected. And all that summed up for all of the W and X. But the thing that I would like you to realize is this is exactly this. So the expected value of randomly choosing a pair and checking if they're connected is the same as actually computing this particular piece of the clustering coefficient formula. And the same trick works in terms of the number of the vertices. So if the vertex is chosen at random, and then this quantity is evaluated for that vertex, the expected value of that is exactly the clustering coefficient. So what that means, we can iterate this particular expression that I put braces around and average that. And if we did that forever, if we did that infinitely often, it would be exactly the expected value, which would be exactly the clustering coefficient. But since we can't do it forever, we'll run it for a certain amount of time and we'll hope that it gets close. So let me show you how it gets close over time.